Hello, dear friends. This is mechanical vibration course. This is the continuation of previous lecture. I tried to cover the introductory part of mechanical vibration, and this is directly continuing from that point. So let's see what today's lesson seems like. So the basic assumptions, actually our intention is to understand the dynamic system modeling and the mathematical background of dynamic system, especially vibrating system. So basic assumptions are required here. The vibrating system is very small. It vibrates to a small amplitude, either that the sine theta function is approximated as theta, and the structure is linear system whose dynamic may be represented by a set of linear second order differential equations, and the structure obeys Maxwell's theorem. This Maxwell's reciprocal theorem must be obeyed, and other laws are obeyed. The structure can be considered as time invariant. The coefficient in the linear second order differential equations are constants with respect to time. And every mechanical system has a frequency at which it like to vibrate. That what we call natural frequency. And the characteristic geometry of vibration or the mood shift of vibration also be considered. The procedures used in mechanical vibration analysis are vibrating system is dynamic system, as we know, for which the variables such as the excitations is taken as an input and the response is an output, which are time dependent. And the response of the vibrating system generally depends on the initial conditions as well as the external excitations. Most practical vibrating systems are actually are very complex in nature. So only the most important features are considered in our analysis. What are the steps required in vibration analysis? The first one is convert the physical system to a simplified mathematical model. So we may have an intricate physical system which consists of a number of subsystems in it, and we must model it to the simplest form in order to analyze easily and determine the equation of motion of that system, and then solve the equation of motions to obtain the response of the system, and then interpreting or interpretation of the results from the physical system. So that can be easily shown here. So we have a physical dynamic system consisting of many parts in it. And then we'll convert this physical system into mathematical model. We model to the simplified model, that is mathematical model. Then we have to drive a governing equation for the system. Okay, then solving the governing equation using various conditions, and then interpreting the results. So how we can do that? Let's take this the most usual system, which is there in the book called SS Rao book. Everybody knows this. Those who have good background on mechanical vibration, they know this system. So this motorbike and the riders. So this is a good example for the physical dynamic system. So here we have the rider, and also we have a suspension system of the motorbike, and the wheels and the ground also there. Again, we can simplify it to some equivalent system. So equivalent mass is the summation of all the masses, the rider mass, the system mass, and the suspension system mass. And then we assume the structure as equivalent stiffness of structure as K equivalent. And the damping system, we have a shock stratus here. So these shock stratus systems, as well as the damper on the tire also there. So equivalent damping systems represented C equivalent. This is a simple 1 degree of freedom representation. And then this is the free body diagram of this system, a simple free body diagram. Okay. Then finally, what we can see the full model like this. So 1 degree of freedom system. Here, mass of vehicle, mass of the rider, front wheel, this suspension system, stiffness of suspension system, stiffness damper of suspension system, mass of wheels, and the stiffness of tire. Okay, this is also for front and the back what we observe. Again, someone can represent it in equivalent manner here. Here, MB plus MR. So let's call it as MR is the rider mass, MB is the bike mass. So this is 2 degrees of freedom, more than 1. So the most usual representation is the simplified form, not such complex. Okay. So finally, we can get an equation of motion, which is mqx dot dot c equivalent x dot plus k equivalent x, which is equal to 0. So m equivalent is the equivalent mass, c equivalent is the equivalent damping system, and k equivalent is equivalent stiffness of all the system. So in similar ways, this example also available in CS Rao book, which consists forging hammer. So there is a forging top here. There is anvil here. Okay, so it is enclosed with some frame, and which is based on the elastic part, which can consider as a damping. And then there is a foundation block here. And then finally soil. So this is the physical model of the structure. And then this can be represented in different method, in single degree of freedom system, or multi-degree of freedom, or 2 degree of freedom system. So the top is considered, which is falling down to the anvil, and anvil and the foundations are taken as one system. And then soil damping, soil stiffness is here, and then soil is there. So this is single body degree of freedom system. And when we come to here, foundation is taken separate, and the anvil is taken as separate. So then we can make analysis. Actually, when we separate, the result which we can get is better, but analysis is very complex. So that is the difference. Okay, prerequisite knowledge is required, especially the knowledge of while we are studying vibration, static mechanical courses like statics, dynamics, strengths of material. These solids mechanics courses are very essential in the analysis, because most of the stiffness calculations, the deflection calculations are easily available on these courses. And then mathematics is the fundamental course for the study of vibration. So the knowledge of mathematics is very essential here. Especially we use trigonometric functions, we use complex conjugate systems or number systems, and fundamentally the linear algebra part, which contains matrix theory, differential equations like partial differential, ordinary differential equations, all are there. And then the Fourier transformations and Laplace transforms are an important part of the course. So in this lecture, I will give emphasis for the mathematical aspect of the course. So I will touch the very important part of mathematics, but that is not sufficient. Somebody or those who are interested in this course must understand the mathematics truly, especially the linear algebra part is very important one. So short summary of mathematics used in vibration analysis, particularly I'll see the differential equations. So when we say equations, these are equations describe the relation between the dependent and independent variables. So in our vibration analysis, there are dependent and independent variables. So this can be easily obtained from the simple equations. Most of the time we use that equal sign for our notation and in equations, like for example dy over dx is equals to f of x. So here equal sign. So this is the first order differential equations. Dy over dx is equals to f of xy. When our variables are x and y, it is f of xy. If we are going to define the equation is given in terms of one variable, f of x, then it is a function of one variable, function of two variables. Or we can represent our equation in terms of sine and cosine function, that trigonometry. X of t is equals to a sine omega t plus phi. X of t is equals to a cos omega t minus psi. And x of t is equals to a1 e the power of, this is exponential function. This is the exponential function. These are trigonometric functions. These are differential equations. And then there is a quadratic form of equations. So we must know how to solve, how to find solution for such kind of equations. Okay, so that is the intention of this discussion. What is differential equation? So that is one of an important part of our study, which that equation that involves dependent variable and their derivatives with respect to independent variables are called differential equations. Actually, we have two types of differential equations: the partial differential equations and the ordinary differential equations. So what is the ordinary differential equation? That is an equation that involve only one independent variable are called ordinary differential equations. For example, here m of x dot m of x dot dot of t plus k of x t is equals to 0. Here x is one of the variables which we are going to determine. Again, here we can represent it in this form: m d square x. The representations are the same actually. This representation represents this one, plus c dx dt plus kx is equals to. This is for forced vibration. This is an equation for forced vibration. This is equation for free vibration with no damping, and this is forced vibration with damping. And also dy dx is equal to f of x. This is first order equation. These are first order equations. These are second order equations. Again, this one is first order equations. So these are ordinary equations. There are various ways of representing the equation. This is one way. This is another way. Again, someone can represent it in this manner. So this is ordinary differential equation representation. Partial differential equations are also equations that involve two or more independent variables, which are within the system of equation. For example, u of x, like du over dx, like the heat equation in the case of heat transfer. Again, u of y, which is equals to du over dx, u of xy. Here we have two variables, two different variables. U of x, again u of y. So du dx is for the u of x, and the du dy is for the. So we are going to solve partially for x and for y, and finally what we can get our required solution. So partial differential equations, these four. Many types of representations are there. We can see, for example, let y of x of t is equals to a cos kx plus wt or omega t. Let this be an equation. Then the partial differential equation of y with respect to x is equals to dy of xt, because this variable is in terms of x and the t. Okay, so dy x of t dx is equals to minus k, because here for x this is the constant. Okay, k is the constant. So ak sine kx plus omega t. Y of xx is equals to d square y, that's second derivative of y with respect to x. Sorry, this is x square, not like this. Okay, which is equals to ak square cos kx plus ut. Yt. Now, in terms of t, dy dt, okay, which is equals to minus a omega sine kx plus omega t, y of tt, which is equals to dou square y xt over, still here there is mistake, dou t square, which is equals to minus a omega square cos. So these are a representation of partial differential equations. Okay, more examples on partial differential equations. We have this heat equation. This is one representation. This is another representation. Similar. These two are similar. Okay. Or this is a combination of representations. This is also another partial differential equation. This is again partial differential equation. Okay. Now, the order and the degree of the equations. We must identify what is the order, what is degree. So the order is the highest order derivative present in the differential equation is the order of the equation. And degree is the highest power of the highest order derivative. The power, again, the highest order derivative may consist some power, the power of some. Okay, so that is called the degree. So for example, here d cube y dx cube plus d square y dx square as a whole square plus dy dx as a whole for the power of 4 plus y is equals to 5. Here our highest derivative is d cube y dx cube. So in this there is by default, power 1. Power 1 is here. Okay. Let me represent it with pen. When is okay? Pointer. Okay, pen. So if I do like this, for this by default there is power 1. So the power is 1 for this, and it is order 3. So third order differential equation is power 1. Okay. So it is the highest order derivative is this thing, and third order and derivative order 3. Now the power of higher order derivative, this is 1, so that is 1. Another, this is the fourth order derivative, order 4, and the power 2. This is the power. This is the power 2. Okay, not this one, not this one. We give emphasis for the highest order derivative. So it is fourth order derivative, order 4, and the power of highest order derivative is 2, so that degree 2. So this gives some example of differential equations of different order. Okay, so here this is the highest order derivative. So it has 1 power 1, and it is first order derivative, order 1 power 1. Here also, this is the third order derivative, but having power 4. So third order derivative with power 4. Okay, again here, this needs some rearrangement of some terms, but after rearranging the term, dz over dx is equal to 1 over y minus 2 cube dy dx. So here it is first order with degree 1. Again here it is first order degree 1. Here third order, we can see this one is third order and having degree 1. It has by default degree 1. It is not this one. When we come to here, it is second order with degree 1. It has no coefficient, no power. Degree by default 1. So 2. Okay. So at the same time, whether they are linear or non-linear, we can identify here. Some of them are non-linear, others are linear. For example, this is a linear equation, and another are non-linear equation, because a1 of y has x as coefficient. So because of that, it is non-linear. Derivative not first power. So derivative is having power 3, so that it is still non-linear. Again here, a1 of y has x as a coefficient, so that it is non-linear. And in this case, derivative not first order, not first power. Okay, so so due to that, it is non-linear. So that is the difference between linear and non-linear. So we can see what linear and non-linear in the next. So linear, non-linear, and what quasi-linear. Actually, quasi-linear is not included here. So linear is a differential equation called linear if there are no multiplications among dependent variables and their derivatives. In other words, all coefficients are functions of independent variables. For example, dy dx plus p of x y, which is equal to q of x. K and the q are function of x. Then we can solve this equation easily using this formula. considering solution y of x, which is equals to 1 over I of x, that I of x is equals to e is the power of p of x. Okay, this p of x is a coefficient of y, q of x is this term, so we can calculate it using. So this is linear type. Nonlinear equations are differential equations that do not satisfy the definition of linear. So, for example, these are some of the linear equations and the nonlinear equations. Here, for example, in this case, second order, but here we multiply it y prime with y. This made it the equation nonlinear. Again, when we come to here, we have this power. Okay, this power. This power also intricates the system of equation, and then it is nonlinear still. Another concept is homogeneous and non-homogeneous system of equations. Homogeneous means a differential equation is said to be homogeneous if every single term constants, the dependent variables are their derivatives. If they have their derivative, then it is homogeneous. For example, mx dot dot plus t plus kx t is equals to 0. Actually, this equation is the most usual equation for the undamped free vibration case. Because of that, I'm using it here. So this equation is a homogeneous equation because this term has no entry. This is 0. So this is linear. This is second order homogeneous equation. This is also second order homogeneous equation. Every homogeneous system has at least one solution known as zeros. Or these zeros are called trivial solutions, which is obtained by assigning the values of 0 to each of the variables. If the system has non-singular matrix, that determinant is of matrix A is different from 0, then it is also the only solution. Let's take this example. Y prime prime plus 9y is equal to 0, or second derivative of y plus 9y is equal to 0, a homogeneous equation, which is homogeneous linear differential equation of order 2, because the power here it is 1, 2. This is order 2. Therefore, if we can find two linear, this needs two linear independent solutions, and use the principle of superposition. Means the two linear independent solutions are required, and those solutions are added up in order to get the final solution. That is superimposing the solutions. We'll have all the solutions of the differential equation. Okay, so non-homogeneous equation of system, for example, x prime 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 x is equal to 0. This is actually homogeneous, not non-homogeneous. What we are talking here is homogeneous. Okay, so x plus t2 plus x is equal to 0. These are constants actually. Y prime prime plus x prime prime plus y is equal to 0. This is still homogeneous. If, for example, this thing is y, immediately the equation becomes non-linear equation. But these all are linear homogeneous equation. Okay, this is also homogeneous equation. So for the previous example, for this example given here, for this one, let's solve. f of x is equal to c1 cos 3x is one of the solution. And then g of x is equal to c2 sine 3x is another solution. Actually, we can find it. We can solve this equation with the help of exponential function. That f of, instead of this, we can also use f of x is equals to which is equals to sum a1 is a power of that is I3 plus 3x plus A2 is a power of minus I3x. With this also we can solve this equation. But let's take the easiest trigonometric relation. These are almost equivalent. Are solutions to differential equation. So cos 3x and sin 3x are linearly independent. They are different. So that therefore, by using the principle of superposition, we have this type of general equation. Okay, this is the equation. Y of t is equals to c1 cos 3x plus c2 cos, and this c1 and the c2 are arbitrary constants which should be determined from the initial conditions or applying some initial values. So let's take an initial values. Y of 0 is equals to 1 and y prime of 0, that is first derivative of y is equals to minus 6. Then we can compute it. Give this y of 0 is equals to, put 0 here, c1 cos 0 is 1. So 1 is equals to 1. That implies c1 is equals to 1. Sine 0 is 0. This term will be 0. So c1 is equals to 1. That means y of 0 is equals to 1. Y of 0 is equals to 1 implies c1 cos 0 plus c2 sine 0. So sine this is 0. So it gives us 1 is equals to c1. Again, the y derivative of this one is 3 times y derivative is equals to minus cos is minus sine, so minus 3c1, okay, sine 3x plus the sine derivative is cos, okay, c2, 3 times c2 cos 3x. Okay, when we apply this boundary, this initial condition, y prime of naught, which is equals to y prime of 0 is equals to 6, minus 6, I mean, minus 6, which is equals to, okay, sine of 0, 0, so this term is 0, plus 3 times c2 cos of 0 is 1. So 3C2 is equals to minus 6, which implies C2 is equals to minus 6 over 3, which is equals to minus 1. So these are the constant values. So substituting these constants, finally we can get y is equals to y of t is equals to cos 3 y of x, actually cos 3x minus 2 sin 3x is the value or the solution for the homogeneous equation. Now let's see, there are various ways of calculating homogeneous and non-homogeneous equations, but let's come to non-homogeneous. Then non-homogeneous one is somehow intricate than homogeneous one, because it consisted the homogeneous equation as well as the particular equations. Anyways, non-homogeneous equations are differential equations which do not satisfy the definition of homogeneous and considered non-homogeneous. So for example, this is non-homogeneous. It is because of the presence of this force function. Okay, so this is forced and damped free vibration equation. For example, this is also another equation, which is the most usual equation, second order derivative. Okay, linear non-homogeneous equation. And non-homogeneous system has an associated homogeneous system, which you get by replacing the constant terms in which equal with 0. For example, if we substitute this part 0, then that the part of the equation is homogeneous. Okay. If we substitute this term 0, these are terms which added non-homogeneity on the equation. So non-homogeneous differential equation, it is now time to start thinking about how to solve non-homogeneous differential equation. Let's consider the second order linear non-homogeneous differential equation. Let's consider this. This is non-linear. Actually, this is linear second order non-homogeneous, and having some terms p of x, q of it is in terms of t, and the part which introduce non-homogeneity, that is g of t, is also there. Okay. So general solution to the non-homogeneous equation becomes y of t is equals to y complementary plus y particular. This y complementary is the solution of y homogeneous, the homogeneous part of the equation. It is we first assign this g of t is equals to 0 in the equation, then the equation becomes homogeneous. So once that is done, the equation becomes homogeneous, and that part is the homogeneous or particular complementary solution. And the particular one is the solution which are related with this one. Most of the time we select the particular solution based on this term of the equation. If this term is exponential, we select the exponential term. If this term is sine function, then we select sine function for the particular solution. If this part is constant, we consider some constant or linear terms, and so on. So that is the part. So homogeneous linear differential equation for the previous one, which is equal to 0, then this homogeneous differential equation. So the solution to the homogeneous differential equation is y complementary, which is c1y1 of t plus c2y2 of t. This is the complementary part. Then the general solution to the non-homogeneous, the general solution of this non-homogeneous this equation is this plus this complementary part of solution plus particular solution for the equation. So these are some of the non-homogeneous equations. Okay, x prime y. So due to the presence of this, it is non-homogeneous. Here also, due to this, non-homogeneity is because of this. So for the sine t, the particular solution will be related to sine t. For this linear 2t plus t, for this equation, this 2t is kind of constant. So we emphasize this type of equation. Again, 6x plus 3, we consider this type of linear equation and trigonometric equation. Okay, let's solve one example in order to understand what is the non-homogeneous equation and its solution. Let's this be y prime prime minus 9y, which is equals to minus 6 cos 3x as a solution, as an equation. It is non-homogeneous due to this term here. Okay, so for this, y prime prime minus 9y is equals to 0 is the type of equation what we have seen in the previous case. Okay, in the previous case, we have seen such kind of equations. Okay, so for that, the y homogeneous, okay, here it is represented in terms of exponential function, but in the previous, this can also be represented with sine function, no problem. Okay, y of x is equals to okay, c1 sine 3x plus c2 cos 3x is also a kind of equation. There, this can be also used. Now, based on the form of equation here r of x, most of the time these non-homogeneous equations are represented in equation of for example y prime plus p of x y prime plus q of x y is equals to r of x. This is a form of equation. So our intention is on the r of x part. So based on the function r of x, which is minus 6 cos 3x, yeah, here r of x is minus 6 cos 3x. So our initial guess, we are just guessing based on our existing the r of x equation. So a cos 3x plus b sine 3x, we consider this one. Okay, this is the considered equation, that is particular solution. So y of x is particular. So solving the complementary equation, this is valid case. Okay. So now we ypx, just first derivative and second derivative of this is gives this to determine a and b. This coefficient a and coefficient b can be determined using this relation. Okay, yp of x, y prime prime of x is equals to this. Finally, substitute these equations, including this. Okay, this one. Sorry. So substituting these equations into the main equation, this is the main equation. What we can get finally? This equation. So here in this final equation, minus 18 cos 3x and minus 6 cos 3x are there. So equating this one with this, we can get b. Okay, so we can get a. That means 18m is equals to 6 cos, okay, and then minus 18 b sine 3 x is equals to 0 because we don't have sine term here. So 0 times sine, we can simply assume 0 times sine 3x. So this is 0. So sine 3 term is equated is 0, so that b is equals to 0. So from that we can get a is equal to 1 over 3 and b is equals to 0. So y particular is equal to 1 over 3 cos 3x. Okay. A is equals to, this part is 0 and this part is 1 over 3. So immediately this is the particular solution. So the general solution for this non-homogeneous equation is y of x is equals to the complementary part of solution plus the particular solution. So this is the type, the method we can use to solve non-homogeneous equations. Distinguishing between linear and non-linear, it's a simple kind of exercise actually. This is an exercise. These are some equations, about 8 equations, okay? And what are they homogeneous or non-homogeneous, linear or non-linear? So we can judge it by looking from the previous what we have learned. Or are they homogeneous or non-homogeneous? Okay, so this is my answer. Okay, so I don't want to see one by one. Someone can see that. Now, another important topic in vibration analysis is matrix operation, because most of the equations are, especially multi-degree systems, are evaluated in terms of matrix. So matrix operation is an important operation in vibration analysis. So system of linear equations can be represented in the matrix form using coefficient matrix and the variable matrix and constant matrix. So let's consider 2 linear equations. Equation number 1, 2x plus 3y. Equation number 2, okay, that is 5x minus y is equals to minus 2. These are 2 linear equations. And someone can solve these 2 linear equations using simultaneous equations method, or back substitution methods, or any kind of methods. A lot of methods are there. But in this, the coefficient matrix is, we can take 2, 3 in the matrix form, and 5 and the minus 1 as a coefficient matrix. And the variables matrix are, the variables here are x and y, so x, y. And then finally, it gives this 8 and the 2. So this is the matrix representation for the 2 linear equations. Okay, this is 2 linear equations, so it's matrix representation. In similar way, we can represent 3 equations. Equation number 1, equation number 2, equation number 3. These are 3 linear equations. A1x plus b1y plus c1z is equal to d1, one equation. This is second, this is R. So the 3 linear equations are represented in matrix form. as this. Okay. So different methods for matrix inversion. Inverting this matrix is a very important thing. We have to invert matrix because in order to get these coefficients or these variables x and y, x, y, z, we must invert the A matrix. This is in the form of A, x is equals to B. X is equals to B. B is this matrix. X is this matrix. And A is this matrix. So AX is equals to B form of matrix. So our aim is to find the unknown X and the Y, so that we must invert the matrix A. Okay, the inverse of matrix is an important equation that is applicable only to square matrix. Actually, a matrix should be a square in order to invert the matrix. Then square matrix cannot easily be inverted. Okay. Geometrically, the inverse of matrix is useful because it allows us to compute the reverse of the transformation. That is, transformations that undergo another transformation. So there are several ways to calculate the inverse of matrix. So some of these are the Gauss-Jordan elimination method, the classical adjoint method, partition method, and other methods also. So the Gauss-Jordan elimination method we use. So Gauss-Jordan elimination is an extension of Gauss elimination. So both algorithms actually used in the matrix calculation. So on that, we use row echelon form or row reduced echelon form of matrix. As an example, we can see that 2 by 2 matrix 1, 3, 2, 7. Okay, so how we can find the inverse matrix using Gauss-Jordan elimination. First, let's write the matrix A. So this is A matrix. This component 1, 3, 2, 7 is A matrix. Then augment it here. This is augmented matrix. And then add the unit matrix 1, 0, 0, 1. This is because 2 by 2 matrix. So we have only 2 unit vectors. So if it is 3, we will add 3. Now, the next is, once we do this, let's reduce the row. Row 2 is reduced to 2 times row 1. Row 2, the entry in row 2 is equals to 2 times row 1 means we can get this matrix here. And this side, we can get 1, 0, minus 2, 1. Again, further, row 1 is equals to minus 3 times row 2. By doing that, we can get 1, 0, 0, 1 here. And there, 7, minus 3, minus 2, minus 1. So here already, the unit matrix this side changed to this direction, implies that the matrix to this side are the inverse of the given matrix. This is the inverse matrix. So the inverse matrix is equals to 7 minus 3 minus 2 minus 1. That is this one. Okay, another one is one can make an exercise on row reduced echelon form of representation using Gauss-Jordan elimination method. This is a simple explanation. Another one is a classical adjoint method. So that adjoint method allows us some transpose of some matrix and cofactors and minors, the concept of minors. Okay, so this all comes here. So A inverse or the inverse matrix is equals to adjoint of A over the determinant of matrix A. Okay, so how we can find the minor for each element of the original matrix? That can be Cij is equals to minus of 1 I plus j, the power of I plus j times mij. What are these mij's? Let's see mij's. mij's are the minors. So I used C instead of M here. So let's see. Let's compute the inverse of this matrix. By taking some particular 3 by 3 matrix, we can easily compute it. C11 means C11 1461. That means when we do like this, let me do like this. We have left 1461. 1461. So which gives 1 times 1, 1 minus 24 minus 23. C12 means we close this and this. That time we have left 0, C12, 0, 5, 4, 1, 0, 4, 5, 1, which gives minus 1. Okay, here there is minus 0 minus 1 is 0, 0 minus 20, minus minus plus, okay, 20. Okay, so by doing this, we can find for all C values. Okay, then the C transpose, this C transpose, C values C11, 1, 2, 1, 3, 2, 1, 2. The transpose of this gives us a matrix C11, C21, C no, not 21, but 1, 2 here, rather 2, 1, 1, 3. Again, the entry here is C, 2, 1, C, 3, 1, rather than the transposed matrix. Okay. So similarly, all entries. So finally, this is the C matrix, and the transpose gives us this value. So now the adjoint inverse is adjoint over determinant. So the determinant of that particular matrix must be known. How we can find the determinant of some matrix? So the determinant of this matrix must be calculated in order to finish this work. So that means determinant is obtained as 1 over 2. So we can see how we can calculate determinant. So finally, this is say A inverse, matrix inverse of A. Okay, so how we can find the determinant of the matrix? Let's see. For 2 by 2 matrix, determinant of A is equals to, for example, if A is this matrix, okay, the determinant of A, B, C, D is equals to AB, AD, BC. AD minus BC is the determinant of 2 by 2 matrix. How we can find determinant of 3 by 3 matrix? A times this entries, A times this entries, EF, HI, minus, this is plus, this is minus, and this is plus. So minus B times, okay, we can handle like this, DG, FI, and C times, positive C times this. This easily gives us the determinant. So Let's take this example, one simple example to find the determinant. 2, 1, 3, 4 minus 1 minus 1, minus 5 to 4 to 6, 9. So what is the determinant of this? 2 times minus 2 minus 1 is minus 1 times 4 minus 1 minus 5, 6, and 3 times 4 minus 2 minus 2 minus 5 minus 2. This gives us minus 45 easily. Or someone can easily find the determinant of some matrix, minus 7, 10, 4, 3 minus 9, 2, 7, 1, 2. For this matrix, someone can find like this. Taking the multiplication of this as positive, minus 7, minus 9, 2. Minus 7 times minus 9 times 2, which gives positive 126. Minus 10 times 2 times 7, minus 140. And 4 times 3 times 1, which is equals to 12. This as positive. And then actually here some augmentation is done here. One must understand. And the I and the J terms are repeated here. This is I, this is J, and this is K. And then these are I term and the J terms repeated. K terms not given. So this gives 7 times minus 9 times 4, minus 252. 1 times 2 times minus 7, minus 14. 2 times 3 times minus 10, minus 60. So we'll add up all of these values. This plus this gives us, actually, for these terms, we subtract these terms. Okay? These terms are all taken as positive. These are positive terms. These terms are taken with minus sign. So minus this, that gives 326. So that is the way how we can find a determinant of 3 by 3 matrix. Okay, matrix inversion again. We can find 3 linear differential linear equations, not differential yet, linear equations of 1, 2, 3. So the system of linear equation will be converted into matrix AX is equals to B form of matrix. Then how we can find or how we can get this X, Y, Z. That is our intention. So calculate the determinant. The determinant of A is this matrix. This is our A matrix. This is our B. This is our capital X. So our aim is to find X. So determinant of A is obtained as 10 here with the same principle as we have discussed. So now determinant is different from 0, means we have a unique solution. The linear system of equations is consistent, means it is different from 0. If it is 0, then this takes us to some eigenvalue problem or other form of equations. Okay, so unique solutions exist for this type of. So Ax is equal to B means X is equal to A inverse of B. So calculate this thing. Let's calculate. So 1 over determinant of A times adjoint of A is the method. So we have done the same question there, so I don't want to repeat it. Everything is the same procedure. So minors are calculated. Then the Cij parts must be calculated. So Cij, which is equals to minus 1 the power of I plus j times mij. So here we have mij 4. So Cij minus 1, 1 plus 1 is 2. 2 square minus 1 square means it is positive. So we can get positive 4. This m is equals to 5, positive 5, and C1 2 means 1 plus 2, that is 3. So 3 minus 1, the power of 3 means, again, it gives minus 1. So minus 1 times 5, minus 5. C1 2, m is equals to 1, that is here, and it is 1 3. 1 plus 3, it is 4. So for even case it is positive, so that it is 1. Minus 2, but 2 plus 1 is 3, odd case. So this will be minus plus 2. It is 0 means already 0. M is equals to 2, and the C2 3 makes the C negative. 2, 3 plus 1 is 4, that makes it positive, so it is positive. Minus 5, 3 plus 2, 5, positive. And 3 plus 3 is 6, so it is positive. So adjoint of the matrix is equal to C transpose, that is directly C11, C12. Okay. C transpose means transposing the C matrix. Okay. So that C matrix from this is I can put C matrix 1 1. C11 is 4. C12 is minus 5. Okay, C13 is 1. Again, C21 is 2. Okay, this is 0. This is minus 2. This is 2, 5, and 3. This is the C matrix. But the transpose of this matrix gives this. Okay. C transpose means it gives the above this equation. Okay, so that is the adjoint. So A inverse is equal to 1 over determinant, that is 10, already calculated, and adjoint is this. Finally, B is this. So X is equal to A inverse B. That implies we substitute all the values. Okay, so X is equals to 1 over 10, 20 minus 10, 10. So which gives X, Y, Z is equals to 2 minus 1 and 1. Or X is equals to 2, Y is equals to minus 1, Z is equals to 1 is the equation. So another is eigenvalue problem. That is the most important part in the vibration analysis of various mode shapes. Okay, so we have to determine eigenvalues and the eigenvector. Okay, we must find the eigenvector. So find the eigenvector and the eigenvalues of the following matrix. This is matrix A. So to find the eigenvector, we must use A minus lambda I. I is the unit vector. That means lambda is eigenvector, so which is equal to 0. The eigenvalues are the roots, eigenvalue actually. The eigenvalues are roots of the characteristic equation. So the roots of characteristic equation of this one is the eigen values. So let's put it in the vector form, v1, v2, and v3 as the vectors in the space, and then determinant of this a minus lambda I. So determinant of a minus lambda I is equal to 0 means the characteristic equation. So let's put this is a matrix, okay, lambda times unit matrix, which implies 3 minus lambda. Okay, the diagonal entries will get lambda values. Okay, because here only diagonal entries are there. So in A terms, minus lambda, minus lambda, minus lambda are there in the diagonal, which is we directly use the same principle as we have seen previous. So 3 minus lambda, this term is taken, and this part. So taking the determinant of this part, okay, minus this plus this minus this plus. So using the same principle, we can find lambda 1 is equal to minus 1, lambda 2 is equals to 8. And we have actually, there must be 3 values of lambda from this equation, but 1 is 0. So lambda 1 and lambda 2 are minus 1 and 8. Okay, so let's take for eigenvector lambda is equal to minus 1. Let's calculate. This is the equation. Okay, let me substitute in this equation instead of lambda minus 1 plus 1 minus minus plus, again here minus lambda minus 1 plus 3 plus 1. So this is the a minus lambda I value of the again based on this this is the equation. Okay, equation having this a minus lambda I times v. Okay. So first, let's reduce the matrix. This matrix, A matrix, can be reduced using row-reduced echelon form of matrix or any kind. By reducing the matrix, we can find v1 minus v3 is equal to 0, v2 minus 1 over v3 is equal to 0, and one term of this matrix is singular. There is some singular term, so that v3 is equal to we let v3 is equal to 1. Once we let this value, the remaining values easily obtained. So substitute v2 is equal to 1 over 1, which is equals to 1 over 2 v1. v3 means it is 1 over 2, and v1 is equal to v3 from this equation. So that is 1, 1. This is the equation. Again, for lambda 8, these are the eigenvectors actually. The eigenvectors are 1, 1 over 2, and 1. The eigenvectors for lambda is equals to 8 is obtained by substituting instead of lambda, this 8, what we can get? Minus 5, minus 8, and minus 5. So this is the a minus lambda. So this is the vector form, and then these are the eigenvectors. So how we can find the eigen? Let's reduce the rows using the row reduced echelon form of matrix. By reducing that, finally we can get this equation: 1, 0, minus 1. Actually, the step start from this equation. Step 1, reduce R2 plus 25 R1 implies R2. In the place of R2, we can substitute this value. Again, R3 plus R4 over 5 R1 in the place of R3. This is the second step. And then this is the third step. This is the fourth. This is the fifth, sixth. And finally, we get 1, 0, minus 1, 0, 1, minus 1, 0, 0, 0. This implies the singularity in the system. So from the first equation, 1, okay, so let's substitute 1, 0, minus 1, 0, 1, minus 1 over 2, 0, 0, 0. So B1, B2, B3 are here, which is equal to 0. This is the reduced form. So V1 minus V3 is equals to 0. And V2 minus 1 over 2V2 is equals to 0 from the second. And this is the term which we consider. So let V3 is equals to 1. Let V3 is equal to, because 0, this shows some singularity in the system. So 0, V3 is equals to, let V3 is equals to 1. Then the remaining equations become 1, 1 over 2, 1. That is also similar to the previous one. Okay. The next important part is trigonometry. So we use some kind of trigonometric relations, like for example, for some right angle triangle, we cite A1 and A2 having an angle of theta. So sine theta A1 over A is the this side, which is equals to A1 square plus A2 square. So that is this side of the triangle. Using Pythagoras relation, we can calculate these things. This is not required here. So some reciprocal identities, trigonometric reciprocal identities, trigonometric identities are there. So these are important part of trigonometry. So variation on the Pythagoras theorem, that sine square A plus cos square A is equals to 1, tan square A plus 1 sec square A, 1 plus cot square cosec square A. Half angle formulas are also here. Half angle formulas. Double angle formulas are also helpful. Again, additional formulas here given, because in most cases we use these things. And laws of sine law and cosine laws. Okay, so these are also helpful formulas. And also double angle formula and half angle formulas, the representations. These are familiar with most engineering students. And what are initial and boundary conditions that are very important in the calculation of vibration? Not only in vibration, but in most mechanical course, these are very important. So initial conditions are constraints that are specified at the initial point, at time point of. Generally, it is time point, okay, are called initial conditions. Problems with specified initial conditions are called initial value problems. For example, when we specify some time, for example, x of t is equals to 0, means at some specific time, then it is called initial value problem. For example, the equation of motion, mx dot plus kx is equal to 0. We specify initial conditions as x of t is equal to, for at time t is equal to 0, x of t is equal to 0, which is equal to x naught. The amplitude of the vibration of this motion at time t0 is x naught, and the initial velocity at time t0 is equals to v naught. Then these are called initial values, and the problem is called initial value problem. Another one is boundary conditions. These are constraints that is specified at the boundary point, especially for the constrained system with some specific boundaries. For example, in the mechanical system, the fixed points. In the heat transfer, the point at where temperature is applied, or at the point where heat flux is applied. Okay, so generally space points are called boundary conditions. Problems specified boundary conditions are called boundary valued problems. The problems are boundary value problems. In the case of initial, they are called initial value problems. Initial value problems, and here they are called boundary value problems. So displacement boundary conditions, temperature boundary conditions, we simply call them as some Dirichlet boundary condition. And force boundary conditions or heat flux boundary condition, we sometimes call them as Newman boundary condition. And some combination of boundary conditions also appear, like Robin boundary condition, especially in the diffusion phenomena. The Robin boundary conditions, which mixes both may be used. Okay, so we can see here u of u is equals to 0, v different from 0. So that means u is 0. Again, in this age, u different from 0, v is equals to 0. Means the y component is 0. In this case, x component is 0. The motion of x is not allowed at this boundary. Motion in the x is not allowed. In this boundary, motion in the motion or application of load is not allowed in the y. So, and also here we can see u different from 0, y different from 0 in this. And there is nx load, distributed load nx is applied to this edge. Okay, so this is in plane boundary conditions. U different from 0, v different from 0. So these are the boundary conditions in the mechanical course. Okay, so this is all about today, and this is the only the important mathematical portions. Actually, exponential functions, Fourier series, and the other mathematical parts like those are not included. But in the middle, when we are playing with the course, we may include other parts of the mathematics, but this is as an introductory, just to give you or highlight you the points of mathematics or application of mathematics in the vibration course. Thank you very much for attending the course.